Today, we're going to talk about a silent, relentless force that's working all around us, all the time. I mean, this thing brings down bridges, it devours cars, and it costs our global economy, get this, trillions of dollars every single year. We are talking about corrosion, but you probably know it by its more famous name, rust.
I know, it sounds super dramatic, right? But here's the thing. In a way, it's absolutely true. Iron, the very backbone of our modern world, has this fundamental vulnerability. From the second it's made, it is trying to get back to its natural, more stable state, how it exists in the earth as ore. And that whole process, that self-destruction, well, that's what we're here to understand.
So let's dig into this fatal flaw a little bit deeper. We tend to think of rust as just, some ugly orange stain. But it is so much more than that. It's actually an active, ongoing chemical attack that is literally eating the iron away.
Okay, so here's the simple definition. Corrosion is just the process of a refined metal breaking down when it reacts with its environment. This happens to lots of metals, but because iron is the most used metal on the entire planet, its corrosion process gets its own special name, rusting.
And this is the fatal flaw I was talking about. The rust that forms as hydrated iron oxide, it's not some kind of protective shield. Nope. It's brittle, it's porous, and it just flakes right off. And what does that do? Well, it exposes a brand new fresh layer of iron underneath to the very same attack. So the cycle just keeps going layer by layer until there's basically nothing left.
So, if we're going to fight this enemy, we need to understand exactly how it works. What are the key ingredients for this whole destructive process? Or to put it another way, what's the recipe for rust?
It's actually a surprisingly simple recipe. It only has two essential ingredients, water and oxygen. That's it. When an iron atom gets exposed to both of those things at the same time, a chemical reaction kicks off. The iron atoms start losing their electrons to oxygen. That's a process we call oxidation. And these reactions ultimately combine the iron, the oxygen, and the water to form that flaky, reddish-brown stuff we all know and hate.
But like any good villain, water and oxygen have accomplices that can make things happen way faster. Take salt, for instance. It acts like an electrolyte, which makes the water more conductive and just puts the whole reaction into overdrive. It's exactly why cars rust out so much faster if you live near the ocean. Things like acid from pollution, high heat, and even physical stress, like a simple scratch or a bend in the metal, all create the perfect conditions for rust to form even quicker.
All right, so now that we get the problem, let's talk about the solutions. For centuries, we've come up with some really clever ways to fight back. So let's take a look at the toolkit humanity has built to defend against rust.
The most straightforward strategy is maybe the most obvious. Just build a wall. If rust needs air and water to form, then just don't let air and water touch the iron. This is the whole idea behind painting a bridge, or putting that plastic coating on a dish rack, or slathering grease on moving machine parts. It's a simple physical barrier.
But what if you could change the iron itself to make it stronger? Well, that's the whole idea behind alloying. By mixing iron with other elements like chromium and nickel, we create something totally new, stainless steel. The chromium in the mix forms this microscopic invisible shield right on the surface, which protects the iron and makes the entire material resistant to corrosion right from the inside out.
Okay, now for strategy that is just incredibly clever. We're going to use one metal to save another. This is what we call the art of sacrifice, where we basically let one metal corrode on purpose to protect a more important one.
Think about old-school tin cans. We coat steel with a super thin layer of tin because it's non-toxic and it protects the steel inside. And it works great, right up until you get a scratch. See, because tin is actually less chemically reactive than iron, a scratch creates this little electrochemical cell that focuses all the corrosive energy on the exposed iron, which makes it rust even faster than it would have on its own.
Now contrast that with galvanizing, where we coat iron with zinc instead. And here's the brilliant part. Zinc is more reactive than iron. So if that surface gets scratched, the zinc basically steps in like a bodyguard. It says, hey, no, corrode me first. It literally sacrifices itself, giving up its electrons so the iron doesn't have to. The zinc corrodes away, but the iron underneath stays perfectly safe.
And don't think this is just some small-scale trick. No way. This exact same principle, sacrificial protection, is used to protect enormous critical pieces of infrastructure. We're talking about attaching huge blocks of more reactive metals like zinc or magnesium directly to the steel hulls of ships and giant offshore oil rigs. These blocks just slowly corrode away over time, sacrificing themselves to keep the entire structure intact. It's amazing.
All right, time for a plot twist. We've been saying that more reactive metals corrode more easily, but there's one really common metal that seems to completely break this rule. And you've almost certainly used it today.
Seriously, think about it for a second. Based on pure chemistry, aluminum is way more reactive than iron. It should corrode like crazy. And yet, we make everything from soda cans to airplanes out of it, and it just stays shiny and strong. So, what's its secret?
The secret is all about the type of oxide layer that it forms. See, unlike iron's flaky, porous rust, the instant aluminum is exposed to air, it forms this microscopic layer of aluminum oxide. And this layer is the complete opposite of rust. It is tough, it is strong, it's totally sealed, and it's bonded super tightly to the surface. It basically creates a perfect self-repairing suit of armor.
And we've even figured out how to enhance this natural superpower. There's a process called anodizing that uses electrolysis to make this protective oxide layer even thicker and stronger. It's why things like high-quality aluminum cookware and architectural parts are so incredibly durable. So what's the big takeaway here? The crucial point is that rust isn't some unstoppable force of nature. It's a chemical reaction. And through clever chemistry and engineering, we've developed an entire toolkit of strategies, from simple paint to smart alloys to sacrificial bodyguards, to prevent it, to slow it down, and to completely outsmart it.
And that brings us to our final thought. We have the science, we totally understand the mechanisms, and we have the solutions. So why is corrosion still such a massive trillion-dollar problem? It's a question that really pushes us beyond the chemistry lab and into the real world of cost, maintenance, neglect, and just the unbelievable scale of the iron and steel infrastructure that our entire civilization depends on. The science is there, but the real-world challenge? That remains. Thanks for tuning in.